Okay, welcome everybody. This is the week 6 webinar. So this is at the end of this week where I'll be at the halfway point officially. So this is the week 6 webinar, and um, the plan today is, as always, I'll answer any questions if you have. I check the chat box all the time, so type things in. I'm going to ask you to type some things in, and then we're going to get into confidence intervals. Confidence intervals, it turns out is a very, very important application. And pretty much the rest of this entire course is applications. So we're going to be using confidence intervals to get this idea. And the idea is it's pretty much impossible to find out the population mean or the population proportion, because if the population were like, say, people in the United States, there's no way you can ask all hundreds of millions of people. So that's what samples are all about. The problem with the sample is the sample is not the same as the population. You're not going to get exactly the same mean or proportion, whatever you're asking, as the population. So the big thing is, how far off might you be? So how confident are you that it's within some range? And that's what confidence intervals will be all about. And that's what we're going to be looking at. So we'll start out with confidence interval for means. And hopefully, you know by now, if we can do a mean, that means the survey question was quantitative. And then we'll do confidence intervals for proportions. Similar idea, except the survey question is a yes-no question. Okay, or it can be thought of as a yes-no type question. And we can talk about confidence intervals. And they're really, really important. Then we're going to get into the sample size needed. So we've learned already that if you don't have more than 30, you can't use the central limit theorem statement that the distribution is approximately normal. But even if you can use it, sometimes if you have a sample that might be 35, you're going to have an error that might be pretty high, maybe higher than you care that you really need. And we'll talk about, if you say, well, how big an error are you okay with? Based on that, we can talk about what the sample size you need to use in order to have a small enough error. And first we'll do for means, and then we'll do for proportions. And it's very important because, again, two things could go wrong. If you sample too many, then you've wasted your time. It's a lot of work to do a large sample. If I asked you, you have to sample 2,000 people for your project, you'd probably drop the class because it's too much work. Okay. But if you only sampled, a small amount of people, then you may not get very interesting data, okay, or not very useful data. So that's what we're going to be looking at. And sometimes we're going to say, well, is it even practically significant? Okay, so if I can say, yeah, I did a survey and now I know that the average weight of Americans is somewhere between 1 pound and 1 million pounds. Yeah, that's true, but I've learned nothing. So that's the idea of confidence intervals and thinking about how big a sample size you need so you have useful results instead of useless results. So hopefully that makes some sense. I do want to mention a few things. One, we're in week 6. And what's important about the number 6? Pop in the chat box. Yeah, it's an even number, which means you have an exam this week. So be ready to take the exam this week. And just to note that, about half the exam will cover weeks 5 and 6, and the other half covers weeks 1, 2, 3, and 4. So it's definitely more focused on the newer stuff. And the word problems are always going to be from the newest stuff, is how I work it. The part that you have to type in my grade. The other is that the projects, they got turned in yesterday, and I've graded most of them, but not all of them. So I have a few more to grade. And I'll tell you the number one mistake, absolutely number one mistake is not having a partner. And it's very clear in the syllabus. I made it clear in every webinar. You need a partner for the project. There is a 25% deduction. It's pretty much impossible to pass, to have a passing grade if you don't have a partner. So not having a partner is a disaster. So I want to let you know, I actually posted, in fact, I can probably show you this. On the discussion, I pinned it. If you go to discussions, and you'll see Project 2 discussion forum. Okay, and that's where you can ask for partner if you didn't already have one, or two, even better, is have three of you for Project 2. Okay, even though you don't even know what it's about, it's you can get partners and do not even think about doing Project 2 without a partner because grades are never good. So that's just a big note is that having a partner is really important. And a lot of you didn't. And again, that's a disaster. So that's really, 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 really important. So please make sure that you get partners for, and best is three of you. Okay. Two's allowed, three is even better. So that's just a note. The other thing that I noticed is I told you that the Thursday before the project is due, yeah, is what I was hoping is you'd all send me your project one draft. And you didn't. Nobody sent it. And I'll tell you, if I don't see your draft, then you're just hoping that you didn't make any mistakes. If I get to see your draft, I'll let you know the mistakes and I'll tell you what you need to fix so you can get a better grade. I want to help you, but if you don't do things like send me your draft, days before, several days before it's due, then the grade is almost never going to be very good. So that's a few, big pointers for project two. So same rules on project two. Partners you need. You want to send me the draft. Um, the last minute to send the draft is 8 in the morning on Thursday before it's due, before the project is due. But I recommend like more like Monday or Tuesday before it's due because you have a lot of weeks. The next project isn't even going to be due until the end of week 11. So like 5.5 weeks from now. So you have plenty of time. But if you wait till the last minute, things can go wrong really fast. So that's just a note about the projects. I want to help you. I want you to do well, but I can't force it. All I can do is look at it and give you the points you deserve from it based on what you've done and also if you have a partner or not. Any questions at all on that? Any questions? Okay, so very important to make sure you have partners for project two. Okay. Next week we'll start talking about project two. It's a little early now because project two is going to be what we're going to be doing this week, next week, and the week after, basically. So you're not quite ready to even start. So that's just a note. So, but what you can do is you can get partners if you don't have them. You're allowed to use the same partners you had for project one. If you had partners, if you didn't have partners, get partners. If you didn't like your partners, you can pick different partners and work with them. But you need partners. Any questions about anything? Any questions? All right. So I have a question for you. It's too sm it's too small to do the first question that I was going to do, so I'm not going to do that. We need to have a pretty large number of people, and we don't today. So I'm going to do the second one. Is I want you to list how many miles do you live from three of your friends? So give me three numbers, three friends you have, and how many miles you live from them. And type in the chat box those numbers. Hopefully you have at least three friends. Most people do, but no guarantees. Okay, so here's an answer we've got. Let me put in the numbers. We had 0.2. Okay, so we have 4 and 5. Okay, so 0.2 miles. That means a few blocks, maybe 4 blocks away or so, something like that. 4 miles and 5 miles away. Okay. Now, I just want to mention something big, and that is this is just an example. It's pretty worthless because our sample size is 3. But if I did a large sample size, it would just take too long to type and go through the webinar and all that. So, so I just did that. We have another one, which is 3, 1, and point 0.7. Okay. And one question you might say is if you look at all of your friends, how many, what's the average number of miles you live from all of your friends? Okay. And, let's say you have a whole bunch of friends. So that's one way of thinking about this. Okay. I'm going to use the first one as the example, the 0.245, because it's good enough to have one example. And what I want to do is I want to do some calculations. The first calculation is X bar. And again, I could probably do this in my head, but I'm going to go to the calculator. It's a lot easier. And I'm going to go to one variable stats. And we have 0.2, 4, and 5. This is a sample. Okay, so it's a sample amongst all your friends, and I'm going to assume you have dozens of friends. And I'm going to hit calculate. Okay, so the mean is, let's call that 3.1, just round to nearest tenth of a mile. No one cares. No one cares about 100th of a mile that you might live from a friend. So tenth of a mile is close enough. So 3.1 is X bar. Any questions on that? Okay, and then we're going to go to standard deviation. That's about 2.5, 2.5 miles. Is that clear so far? And then we have the standard error. Remember the standard error, the formula for that was sigma over the square root of n. Okay, we don't know sigma. We don't know the standard deviation of the whole population. So we're just going to make a guess. And our best guess is the 2.5. So I'm going to use 2.5 as my best guess. For the standard deviation for, how far away your friends live from you. Okay. And again, 2.5 over square root of 3. I can go over and plug that in. 2.5 divided by the square root of 3. And I get about 1.4. Okay. And again, I rounded to the first decimal place. Normally you'd go more digits, but it's good enough to, we're not really using this. We're just using it for understanding. Any questions so far on getting the information that I want and using what I learned, what we did last week? So essential limit theorem, which said that the standard error is the standard deviation over the square root of the sample size. Any questions about any of these calculations? Not too bad. Okay, so what I'm going to do is say, well, here is my best guess for how far away the average distance all of your friends live from you. And that is 3.1 miles. How good a guess is it? Do you think that is the true average distance of all your friends? What do you think? What do you think? Do you think that's the true average distance? Okay. It's almost certainly not the true average distance. But what we can do is we can say, well, do you think the average distance might be, say, 15 miles? What do you think? Do you think the average distance could be 15 miles? Because we know it's probably not 3.1 exactly. And the idea is the standard error is only 1.4. If I said 15 miles, that's like almost 12 miles away from X bar. And that's going to be many, many standard deviations away, which is very unlikely. Does that make sense? So it's not going to be an average of 15 miles. Even with a small sample size, 15 miles is almost certainly not going to be the true population mean. Is that clear? We're not going to know the true population mean, but at least we can make a guess. And we can say, yeah, our best guess is 3.1. We're off by a little bit, but not by that much. So the big question is, when I say not by that much, what does that much mean? Any questions on the idea there? Okay, this is where we use the central limit theorem and some more stuff that I'm not even going to talk about in this class because there's higher level math we don't do. So what we're going to do is we're going to draw a picture. Okay, we're going to assume we have a normal distribution. Again, in normal cases, you can have a sample size that's over 30. So then you can use the central limit theorem and know you have an approximately normal distribution for the sampling distribution. Okay. You would never have a sample size of 3 anyway for anything that you care about. Okay. But if we had a normal distribution, then the curve looks like this. Nice bell-shaped normal curve. X bar is going to be our best guess, so we'll put that right in the middle. Then what we're going to do is we're going to say, how confident do we want to be? So for example, if you were in charge of a news station, how confident do you want to be? Okay, you can't be right 100% of the time. But what percentage of the time do you want to be right? What's your thought? Any ideas? Maybe you can pop in the chat box. What percent do you think you would want? You'd be comfortable being right, which means that 1 minus that percent or 100% minus that percent, you're going to blow it. And you're going to cite false news. Okay. So you said that maybe 90%. Okay. And that could be possible. Okay. I will tell you for news, the standard has been set at 95%. Okay. The standard has been set for news. The standard has been set at 95%. And I'll tell you, almost 100 years ago, that was set. And it was set by the New York Times. Okay. Before there was even television. And it's never changed from that. Okay. So you'd want to be right 95% of the time. Okay. Kind of similar. What if instead of news, what if you want to do a study about, let's say, to find out if some medication might kill you? Okay. And would you be comfortable if there was a 5% chance that you were wrong and it ended up killing people? What do you think? Yeah, hopefully not. Okay. So there are times when you're going to want, instead of a 95% confidence interval, maybe a 99.9% confidence interval. So you're just right almost all the time. There's also times when maybe you only want to be right, 90% of the time. Okay. Because it turns out that if you want to be right 95, a high percent of the time, then A lot of times you can't even make a statement because you don't have a large enough sample size. Okay, and that can happen. So for example, I would be very happy if I ended up making a whole lot of money in the stock market for 90% of the stocks, even 80% of the stocks that I bought. Does that make sense? So if 80% of the stocks I bought made a huge amount of money, but the other 20% lost a bunch of money, I'd be okay. Okay, so you have to decide what the confidence level should be. Does that make sense? Okay, so once we've decided, then you can draw this picture. And we're going to shade in. So if you want a 95% interval, I just shaded in 95% of this area. And that makes the probability of being right 95%. And then what you do is you say, well, how far left and how far right do you go? That distance from this X bar to the right or the left, because it's symmetric, is very, very important. Okay. So that distance is your margin of error. You've probably heard those words before. That's what that distance means. That's the margin of error. And it's how far left and right you should go so that you have a 95% chance of being correct if you're going to do a 95% confidence interval. Any questions on this idea? Okay. Here's a big note, and this is important. So the central limit theorem does say that sigma sub x bar equals sigma over root n. But do we know sigma? Do we know what sigma is? We don't. We know S. We know the sample standard deviation. We do not know the population standard deviation. Okay? We just really don't. And there's no way you'll ever know. Okay? When you have a very large sample, when you have a very large population, you can't know everybody. So we're going to have to like use S instead of sigma. Okay. Now it turns out, this is one of my favorite stories, the the way of handling the fact that we're using S instead of sigma and kind of increasing kind of the error bounds that we've got so that we can handle that extra is all about beer. I'm sure that's what you're all thinking, right? Turns out there was a statistics professor who also worked as a consultant for a brewery and realized that if they use the normal distribution and kind of did this formula with the central limit theorem, then they weren't right 95% of the time, even though the area said it was supposed to be. And this person realized that the reason was this sigma, is that you don't know sigma and you're using S, and there's an extra error because of using S. And this statistics professor slash brewer, beer guy, decided to name this kind of idea after his students. And he called it the students' t distribution. So when you don't know the standard deviation of the population, which is pretty much always, you can't use the normal distribution exactly. You're going to use something called the student's t distribution. It looks almost the same. It's a little bit wider. That's all I can tell you. I'm not going to get into details. The math is way too hard to explain in this class, but you can trust me. I've done the math. It's fun for me, but most people would hate it. And we're going to use the student's t distribution because of that extra error in using the sample standard deviation because you don't know the population standard deviation. Any questions on that idea? All right. So now what I want to do is I want to say, well, what how far left and right, what should the lower and the upper bound be so that it have a 95% chance of being right? Does that make sense? Any guess on how I'm going to do that? I'm hoping you can guess. Guess? Don't see you jumping in. Here's how I can do it. I can go to the calculator. Isn't that what we always do? I'll go back to the calculator menu. And any guess on which calculator I should use? Should be a number between 1 and 25. Yes. Don't see you jumping in. Okay, so we want a confidence interval. And I'm going to use what we originally had, which was the three values you gave me. So that's going to be a confidence interval for a mean, right? It's a mean because we have quantitative data. And I'm going to use the data. So I'm going to click on that. It's pretty simple. So the data I'm going to use is what you gave me, which is 0.2, 4, and 5. And don't forget to separate by commas. Okay. And let's use a 95% confidence level. And just let you know, so when you're doing news, almost always 95%. The other thing, if you're doing social science, sociology, psychology, that kind of stuff, you also almost always use 95%. Those fields usually use 95. Okay, there are other times you use something different. And I'm going to hit calculate. Was that pretty easy? Okay, then we just read what it tells us. Notice it also gave us X bar and S. So, I did it with a different calculator, but I wanted to make sure that this showed it to us. Um, we have a lower bound of negative 3.2 and an upper bound of about 9.4. Okay, any questions on that? It also shows you the picture, the graph. Okay, and by the way, this is actually not a normal curve. This is a t-distribution curve, but it doesn't look that much different, does it? That's just a note. So negative 3.2 and a 9.4. So negative 3.2 and 9.4. Okay, and I just want to let you know for just looking at this, just because there are some things that can't happen. Can you have a friend who lives negative 2 miles from you? Right? That can't happen, right? Can't live negative miles away from someone. So this negative 3.2, yeah, that is the lower bound, but you can get away with saying that the lower bound is 0. And that would mean they're your roommate, right? That could happen. Okay, so there are different things that could happen. So now let me talk about how we can take these numbers and interpret them. This is really important. So with 95% confidence, we can conclude that the population mean distance that friends live from a person is between 0 miles and 9.4 miles away. Okay, and that is how we interpret the confidence interval. Notice I highlighted, maybe I'll bold it also, the word with, because that's how we start it. If you don't start with the word with, guess what'll happen to you? In our class? Yeah, you lose points. I want to make sure you watch the webinars. So this is one of the ways I force you to watch the webinar is I'll throw some words in the webinar and say you have to use them. You have to use them to get, full credit. So with 95% confidence, if you don't use that word with, you lose points. Okay, again, I'm not trying to be mean. I just want to make sure you're paying attention during the webinars. Okay, any questions on interpreting this confidence interval? Any questions? Okay, so then that was the interval. Then there's the confidence level. The confidence level in this case is 95%. Okay, or 0.95 you'll sometimes use. So that 95% is the confidence level. So how do we interpret the confidence level? And here's what we can do. And again, it has to do with this normal distribution we're looking at, or this guy actually is even better. So what this means is we have a probability, right? This is a 95% probability of being between these two numbers. But what it really means is that we're talking about a probability based on a standard error. We're talking about taking samples and we're looking at the sampling distribution. So given that we had a sample of a certain sample size, in this case, size 3, if you looked at every sample of size 3, then they're all going to give you confidence intervals, right? And I'm going to say some of those confidence intervals are going to be successful, and some of those confidence intervals are not going to be successful. So let me explain what successful means. Okay, let's suppose, just pretend, because I have no idea actually, let's suppose that the average distance that friends live away is 12 miles. Then this is really unsuccessful. How come? Why is this unsuccessful? Or why are we misleading people is another way of saying the same thing. If we're saying that we're 95% confident that the average distance is between negative 3.22 and 9.36 miles, then people are going to think the range should be in there somewhere. Okay, that's what we're going to say in the news is that, hey, somewhere between, 0 and 9.36 miles is where people live from their nearest friend. Okay. But actually, it was 12 miles. It was wrong. You see that? So the idea is that you can do this. Let's suppose, you were in charge of, doing data collection for news or something. Then there's going to be a whole lot of news articles that use your stuff. 95% of them are going to be successful, and the other 5% will be misleading. Any questions on that idea? So now let's write down or talk about how we interpret that. So we say if many samples of sample size 3 are taken, because we have sample size of 3, then each one will result in a different confidence interval. If you had looked at 3 different friends, you'd have a different mean, right? 95% of these confidence intervals will contain the true population mean distance that friends live from you. The other 5% will not contain the population mean distance that friends live from you. Any questions on that idea? Any questions? Okay. So one thing I might ask is that, you know, why don't you just be 99% confident? Because then you would be wrong a lot less often. Okay. Where do you lose out if you decide you want to be 99% confident? Any thoughts? Okay, why? There's pros and cons of the confidence level. What are the issues with only being 90 if you want to be 99% confident? Any thoughts? Might help to look at it. Instead of 95%, if I turn this into 99%, and remember we had 3.2 and 9.4 or so, and they calculate, now it's going to be negative 11.4 to 17.6. So all of a sudden, yeah, I'm very confident, but look how wide a range this is. This is kind of not very helpful information. Does that make sense? On the other hand, if I wanted to be 90, if I were okay being 90% confident, I don't need to be right that often, and hit calculate. Now it's a much smaller. Now it's only negative 1.2 to 7.3 miles. So the pros of having a high confidence interval is that you're going to be right just about every time. The cons is you're going to end up with a very wide margin of error and you're not going to have a very useful data, right? I could be 99.99999% confident and say that, hey, average distance from friends is somewhere between 0 miles and 1 billion miles. Yeah, that's true, but that tells you nothing, right? Any questions on that? Okay, so it's very important to know the difference. What if you wanted to be 99% confident and still have a small margin of error? What would you have to do? Any thoughts? And we'll get to it later today. What would you want to do if you want to be 99% confident and still have a small margin of error, not widened out? Have to add sigma. You can't change sigma because you can't change the standard deviation of how far friends live, right? You can't force friends to live closer to you. Does that make sense? Because that's what you'd have to do to, decrease that. Here's what you would do. You get a bigger sample size. Instead of asking 3 people, maybe you should ask 20 people. Do you see that? If you asked a whole lot more people, then the sigma over root n all of a sudden becomes a lot smaller because n is a lot bigger. Okay, so the solution to having a small margin of error and have a large level of confidence is to have a large sample size. The issue, of course, is that takes a lot of work. Okay, let me do a true example. And by the way, I have a template with whatever percent confidence. It can be concluded that the population mean whatever is between those two numbers. And by the way, it'll be sometimes proportion instead of mean. We'll get to that next. And I have a template for the confidence level, and that is if many samples of however many are taken, each would produce its own confidence interval. A certain percentage of these confidence intervals will contain the true population mean of whatever we got, and some other percent won't contain the true population mean. Okay. So that's a template that will help you kind of do things in, most contexts. I want to mention the word mean is dangerous because sometimes it'll be proportion instead of mean. And that's the next thing. And just to note, since we use the central limit theorem, you need a sample size over 30 if you don't know the population distribution is normal, and you almost never do, by the way. Okay, you ready for a current event? I always like to bring those in. One nice thing about the webinars versus like the old videos. Old videos aren't current, but the webinars are. And I actually just went online and looked up, hopefully you haven't had your head in your sand and you know that we have a new president of the United States. One thing I will never tell you to do is who to vote for, who to like, or anything like that. But I can talk about statistics. That's all I'll do. So one question that the news had was what percentage of adult Americans, of all adult Americans, think that Trump has done a good job so far in this term? Okay, that's a good question. Do you think we can ever find out the percentage of all adult Americans who think that Trump has done a good job so far in this term? Can we figure that exactly out? Yeah, not a chance. Because there's, again, hundreds of millions of adult Americans. There's no way anyone would have the time to do that kind of survey. Okay? Good luck finding everyone, too. So what they did is they took a sample. Okay, and that's how all this stuff works, is you take a sample. And here are the results, and this was a Gallup poll. Okay. One thing I like about Gallup is they tend to give all the information you need for doing statistics. So they asked 1,001 adult Americans. 46% of those adult Americans think that Trump has done a good job so far in this term, less than half. Okay. All right. Note that's P hat because the survey question is, do you think Trump has done a good job so far in this term? Let's see if you can answer. Answer the survey question. If you don't feel comfortable, just make it up. Yeah, notice you're not going to say 73. You're going to say yes or you're going to say no. This is a yes-no survey question. Is that clear? So it's going to be about proportions, not about means. Any questions on that? Okay, then the number of yes answers is going to be n times p. In this case, it's 0.46 times 1,001, which is approximately 500. That's right, it's approximately 460. And that is clearly greater than 5. So hopefully you remember last week, it's not about being bigger than 30 when we have the yes-no answer. It's about having NP and NQ being greater than 5. Then if we want to find the number of no answers, we're going to take 101 minus 460. Okay. And that is 541. And that's certainly also bigger than 5. Okay, and I rounded to the nearest whole number is what you should do, especially with these kind, because you can't have a 0.3 people. So rounding is the right thing to do when you're talking about number of yes and number of no's. Any questions so far on this? All right, so the next thing is let's find a confidence interval. Okay, will this calculator work to find a confidence interval? Will this one work? For the example we're doing, what do you think? Yeah, this won't work because this is for means. Okay, this is for means. There was an X bar and an S. We're not going to have an X bar and an S. Okay, so I'm going to go back to the calculator menu. And what calculator should I use? Yeah, 12. So we're talking about proportions, and we want a confidence interval for proportions. Okay, and by the way, I told you that we're pretty much the end of this week. We're halfway through the class. And guess what? 12 times 2 is 24. We're also going to do 13 today. So we're like halfway through the calculators. Do you see that? I try and make it, ordered correctly. So I'm going to go confidence interval for proportion. Our n was 1,001. Our x is the number of yes answers. And if you remember, the number of yes answers was 460. And since this was news also, probably 95% is about right. Just to let you know, in our class, we're going to use 90%, 95%, and 99%. Those are kind of the three most standard percents that people use for the confidence level. So those are the three that we'll use. So 95% will be standard. If you need to be more confident, then you should use 99%. If you're okay being less confident so you can decrease the margin of error, then you can use 90%. So that'll be our class. And that works for most all studies that anyone ever does. Not 100% of them, but most of them. So I can go 0.95. Okay. And hit calculate. And there we go. Okay. We have our lower bound and upper bound. By the way, p hat was 46%, which good. That's always good to double check that. So 0.4595 is basically 46%. And our lower bound is about 0.43 or so. Our upper bound is about 0.49. And you can see the picture of that. Any questions on this? Okay, so 0.43 and 0.49. Okay, so that's our confidence interval. Okay, margin of error, by the way, just a note, is the distance between your p hat and the either bounds, lower or upper bound, because remember there's symmetry. So either way you go, you'll work. You could also take the distance between the upper minus the lower and divide by 2. Okay, those are choices that you can do, and those will work. Any questions on that idea? Okay, so the margin of error here, notice that we had a 0.46 or 46%, and 49% is 3% above. So the margin of error is 0.03. Sometimes you'll see it written as plus or minus 0.03, and I'll accept either. And that's kind of how far off from our sample mean are we guessing that the population mean is up to with that level of confidence. And that's what the margin of error is all about. Any questions on these ideas? Okay, so now we can interpret the confidence interval. Remember the word with? We're still going to start with the word with. With 95% confidence, we can conclude that the population proportion, just want to note, if you don't have the word population, I will take off points. Okay, you're not confident about the sample. You're confident about the population. Okay, and that's true also for the for means, population mean, if it was a quantitative question. So the population proportion of all adult Americans is between 0.43 and 0.49. Another way of stating the same thing is with 95% confidence, we can conclude that between 43% and 49% of all adult Americans. And then we should think that Trump has done a good job so far in this term. And I guess I should say, just a minute, of all adult Americans. So for the original one, I should say population proportion of all adult Americans who think that Trump has done a good job so far in this term is between 0.43 and 0.49. So it's kind of two ways of saying the same thing. Any questions on the confidence interval? So one is using percents and the other is using decimals, and either way works. Sometimes percent is a little clearer to people, the general public, because they can handle that. They're used to finding out the percentage of something. Okay, we can now talk about the confidence level. Same idea. If many groups of 1,001 adult Americans are surveyed, then each group will result in its own confidence interval. So if we asked a different 1,001 adult Americans, we're going to get a different confidence interval. Okay, and we can do this over and over and over again in theory. And they're all going to give you a different confidence interval. 95% of these confidence intervals will contain the true population proportion of all adult Americans that think Trump has done a good job so far in this term. Any questions? Any questions on interpreting the confidence interval? That was the first piece, and the level, the second piece. Any questions? I want to let you know there's no short way of writing this. Okay, you're going to have a lot of words. So that's very important. Make sure you're ready for the exam because you're going to have to write that kind of thing. Won't be about, thinking Trump has done a good job so far in this term. It'll be something else, but you have to write something. Okay, it's going to have the kind of the same template, but it'll be about something different. And the first, and either of these work is for the confidence interval, and the second is for the confidence level. Okay, there's a lot of writing in this class, and that's important. And by the way, not just for the exams, but also for the discussion post assignment. Make sure you use the template. Okay. Any questions so far? All right. What I want to do now is give you the secret word. We're not even close to done, but I want to make sure that people are actually watching the whole webinar instead of going to the end. So kind of going at, 2/3 of the way or so through. The secret word of this week is population. As I mentioned, if you don't use the word population in talking about the confidence interval, then you're going to lose points. And if you don't remember the secret word is population, then you'll lose points. So population is our secret word. It's now going to talk about more stuff. Okay, so I changed a little bit instead at the end. I want to make sure people who are watching this not live, just don't go to the end to find the secret word and not pay attention to the video. So that's why you didn't put it at the very end. Okay. So now we're going to look at the sample size for a mean. So I want to remind you about some formulas. Okay. The central limit theorem says sigma sub x bar is equal to sigma over root n. Okay. That was the big theorem we had last week. Very, very important. We want to decide how big a sample size we need. Okay. If we want a margin of error not to be too big, and we know the standard deviation. Okay. So what we can say is the margin of error turns out to be Z times sigma sub X bar. Okay. And that gives us Z sigma over the square root of N, plugging in. And then we could do a little math. We can multiply by root N, divide by E, and square both sides. And you get N equals Z sigma over E, all squared. Any questions about the formula? Notice you want a small margin of error, you're going to need a big sample size. Because if you divide by a very small number, you end up with a large number. Okay? So that's important to note. Okay, so here's an example. Suppose you wanted to find a 95% confidence interval for the population mean hourly wage of nurses in California. Okay, might be something you're interested in. Maybe you want to be a nurse. You want to say, how much money am I going to make? Okay. Well, what you need to do is you need to survey a bunch of nurses, right? And ask them how much money they make. You don't want to survey 20,000 nurses, that'll take too long. How many nurses do you want to survey? And this is what we're going to be doing. So based on a preliminary study, so let's suppose you asked, 25 nurses or so, and their standard deviation was $25 an hour. Okay, if you want a margin of error of no more than 50 cents, okay, usually when you're looking for a job, you're not going to care that much whether you make, $75 an hour or $75.50 an hour. So we're going to say, hey, let's let the margin of error be 50 cents. We'll be happy enough. Does that make sense? You wouldn't want a $100 margin of error because that'd be a huge amount of money in terms of, income. Does that make sense? But 50 cents an hour is not that much of a difference. So how many nurses must you survey? Any questions on this idea? Okay, so there's two ways of doing it. One is we can plug it into the formula. What's another way of doing it? Any guess? It's just a guess. What's your guess on another way to do it? Yeah, we can use a calculator. Okay. So I'm going to go back to the calculator menu. What calculator number am I going to use now? Not 13 because that's for a proportion. We want to find out the mean salary for nurses, not the percentage of nurses that get something, but how much do they make? That's a number. Does that make sense? So it's not 13. Yeah, it's 11. We want sample size for a mean because the survey question is how much money do you make an hour? And an answer might be, I make $75 an hour. It wouldn't be yes or no. So sample size for a mean. It's very important to keep that in mind. This entire course from now on, you want to be thinking about that. What is the survey question? Is it yes, no, or is it a quantitative? Okay, then it says, what was sigma? That was given. So we said that standard deviation is assumed to be $25 an hour. So sigma is 25. Any questions on that? E is margin of error. Okay, and we want it no more than 50 cents, 0.5. Confidence level, we want a 95% confidence interval. So that's going to be 0.95. And I calculate it. Was that hard? No. I do want to let you know, if you don't use my calculator, it's a lot harder. And in fact, I'll be honest, there were some faculty at different colleges that were angry at me because they said I made it too easy. And they were worried that their students wouldn't learn the algebra and use algebra, but it is what it is. Students aren't usually math. But I did have some people angry at me because I made it too easy. So hopefully you agree this is easy. So we have 9,604. Okay, which would be a lot. So that means if you really needed this, you would have to spend a lot of time conducting the survey. Good luck surveying 9,604 nurses. Does that make sense? So sometimes you look at this and okay, I can't do it. Okay. Sometimes you look at it and say, well, maybe I'll be okay with a bigger margin of error. How about $2 an hour or something like that? Any questions on that? Okay. So sometimes you're going to want, instead of a sample size for a mean, sometimes you want a sample size for a population proportion. Okay. Notice, just a note, when I did this mean, we said the standard deviation was assumed to be $25 an hour. Okay, that's a big, ugly assumption, and sometimes you don't know. So that's a big if. So the way you can kind of like guess at a standard deviation, one is to do a small study instead of 9,000, maybe you ask 40 people and use that as a best guess at a standard deviation. Okay. So that's one way of handling it. The other way is to just kind of think about what the range might be of kind of, most nurses and then maybe divide by 4. And that'll be the approximate standard deviation. So there's lots of different ways of thinking about it. So that's just a note. In the real world, this finding the standard deviation could be really hard sometimes. Okay, so that is really important. Okay, when you have a population proportion, sometimes you have no clue what the population proportion is. You don't have an estimate. Sometimes you do have an estimate, sometimes you don't. Okay, so let's do an example. So let's suppose that you want to find a 99% confidence interval for the population proportion of cars in the United States that are electric vehicles. Okay? Sound like a good thing? If you want a margin of error of no more than 3%, how many cars must you look at? Sound like a good question? Okay. Will this calculator work? Yeah, no, this is for a mean, sample size for a mean. And we need to go back, and yeah, it was your original guess on the last one that you made a mistake on, but now we want a sample size for proportion. That's number 13. And notice we really are halfway through the class now. Okay, do we have an estimate for the population proportion? Do we have an estimate for part A? Does anywhere here give you any idea what the population proportion of electric vehicles are in the United States? Okay, nowhere on what's highlighted. Nowhere does it show the population proportion. So we have no estimate. So we're going to click or keep that no estimate for P. We wanted our margin of error, notice, to be no more than 3%. So that's 0.03. Our confidence level, we wanted 99%. So that's 0.99. Any questions on that? And they calculate in. And what we need to do is we need to survey 1,844. So the answer is look at 1,844, 44. 44 cars. Any questions on this? Okay, this is to see what the proportion is this year for EVs. All right. So now let me give you something I actually did before this webinar, about 2 hours before, maybe actually more like an hour and a half before, is I went online and I said, all right, well, what were the proportion of cars that were electric vehicles last year? And I did a little Google search, and last year's data, it said 8% of all cars were electric vehicles. Okay. Is that going to change, do you think, how many cars I now need to look at? Because I know what last year was. Okay. And the answer is yes. Yeah, you're right. It's going to change it. Because now, instead of no estimate for P, now we have an estimate for P. So I'm going to click have an estimate for P. And now the calculator is going to say, hey, what is your estimate for P? And that was 8%. We're going to use last year as our best estimate for what percentage of the cars are electric vehicles. Does that make sense? And now I can calculate N. It changed a lot. So by the way, if that estimate for P is very far from 50%, so this is 8%, then you're going to have a big change in the sample size needed. Turns out if your estimate for P is close to 50%, then you won't have much of a change. And if it's exactly 50%, you'll have no change, it turns out. And there's some deep math involved, which I'm not going to get into, but you can believe me. So 543. So look at 543 cars. Notice big difference. So it'd be a lot easier if you had an estimate in this case than if you didn't, when the sample size is far, and when the estimate is far from 50%. Any questions at all? Any questions at all on this idea? So do you believe me that the confidence intervals are very important? They're used all over the place. Okay, it's really, really important. Okay, it's used in so much literature. Okay, almost every published paper will have some confidence interval cited, and so will a lot of other things. It's really, really important because it doesn't just give you an estimate of what something is, it tells you how reliable that estimate is, how far off the estimate might be. Any questions on this idea? Okay. And although we're not quite ready to get into any details yet, I do want to give you a heads up, and that is project 2. A big part of it will be confidence intervals. Okay, another part will be something else that comes next week and the week after. So we're not ready to start project 2 yet, but I do want to let you know project 2 is going to be very different than project 1 because it's going to be the new stuff. And it's confidence intervals is a piece of it. Turns out we're going to do confidence intervals for a comparison study, which we don't know how to do yet, not for another 2 weeks. But confidence intervals are very important. You're going to have to do all those things we just did. You're going to have to decide on the level of confidence and explain why. You're going to have to come up with a margin of error and explain how that, it can be interpreted and used. You're going to talk about the lower bound of the confidence interval and say, well, how can that be interpreted and used? Talk about the upper bound of the confidence interval and see how that could be interpreted and used. All kinds of different things with confidence intervals. So that'll be a big part of project 2. We're going to spend this week and also 2 weeks from now on confidence intervals. So there's going to be a lot of confidence interval stuff coming. Any questions at all so far? Okay, so that actually is it. And that's the end of our webinar. I'm going to stop the recording. And hopefully this made some sense and you realize how important this all is. So I'm going to stop the recording.